sheet metals underneath, and they've just taken a gold solution and attached a wire, run a current through it, and gold winds up making a thin layer onto whatever the metal that they started with was. And at first it looks beautifully, like, wow, look at that gold ring or gold watch. It's beautiful, I can't wait to wear this. And you wear it a few times, the gold wears off because it's real thin plating. So guys, please, don't get gold-plated stuff for the girl. Spend the money and get real, like 14 karat gold, or don't do jewelry. It's better than doing gold-plated, because after just a couple of times wearing it, it really looks like you're a cheapo. Because all the gold is worn off and it looks bad. And even worse, probably has a lot of copper in it, which turns her skin green. Not only does the jewelry look ugly, she's got green skin. Seriously. So no gold-plated ever. All right, now what we're going to do is we're going to have to calculate how much, what mass of the metal plates onto the cathode. And I'm paying attention to the cathode because at the anode, stuff is oxidizing, so you have metals that are going into the solution. But at the cathode is where the electrons come in and the ions will grab onto it, and we would say plate out. There's a lot of car components and other like tool components that are actually painted by electrolysis. This is really common. You get a good coating of a protective material sometimes with electrolysis rather than like brush painting or spray painting. So the amount of metal that's going to plate onto the electrode is all dependent on how many electrons the power source is sending over. The more electrons that come over, the more ions of zinc are able to reduce. So the more mass you get. So I need to show you the calculation. Now this is a stoichiometry kind of calculation, and we're going to wind up with a 5-step stoichiometry process. And at first you think, 5 steps? Whoa, that's too many. But I find this to be one of the easier things, and not just my opinion. When we do the quiz and the test, this is not a difficult thing for students either. People tend to do very well on this section, where you have to calculate how much plating happens. So what we have to do is, first of all, if I could just move this up for a second. One thing that we haven't talked enough about, I know we talked about what a volt is. A volt is a joule per coulomb. But then current also comes in and plays a big part of this. When we do electrolysis, we're going to want to measure what the current is. And current is measured in amperes, or amps. You've heard of amps before. An amp is a coulomb per second. So what that's going to do for us, if we know the current and we know the time, we'll be able to figure out how many coulombs of charge came into the cathode. And if you know coulombs of charge, we got this Faraday constant that relates charge to how many electrons came in. So that's what the 5 steps are, just kind of working our units so that we can eventually figure out what mass of the ion got plated out. So this is the 5 steps. I'll just be quiet for a second and let you write that down if you want to. I got 2 examples for you, then we're going to quit. Everybody good with that? Okay. We there? We finished? So we're going to start with a pretty simple example. It's just very straightforward, goes right along with those 5 steps that I gave you. I'm actually going to do this so that I can't write on the smartboard. I'll write to the board, the whiteboard on the right. But just take a look at this first. What mass of, this just has part A, so what mass of cobalt can be produced in 1 hour with a current of 15 amps? So we have a solution of cobalt-2 ions, probably like cobalt-2 chloride or cobalt-2 nitrate. And so we have that in the cathode. There's electrons coming in. The electrons coming in at a pretty good clip too. 15 amps is high current. We're going to do a lab on Monday. It's an electrolysis lab, and the current we're going to use is 0.1 amp. So that's going to be plenty. You're going to see things happening with 0.1 amp. So if you can imagine 15 amps, I mean, there's going to be serious reduction going on. That's a lot. Okay, so I'm just going to move this over here. Okay, hopefully that's going to focus. So you saw there's 5 steps to the stoichiometry that we do. First step, get your time, if it's not in seconds already, into seconds, which is not bad. We have 1 hour to start with. Did it stop? No. Okay. Just a big fuzz? Okay. Is it good? Thank you. All right. So get the 1 hour into seconds first. And the reason we need to get into seconds is because, remember, the amp is a coulomb per second. So we're going to have to work that out to cancel the time out. So we know how many seconds are in an hour. Right? 3,600. So we have 1 hour down here, 3,600 seconds up here. So seconds now is our current unit. And now from here, we can relate that to coulombs through the current. Now the current, in this case, was 15 amps. So I'll just put it up here. Remember that. And because that means there were 15 coulombs every second. So that takes our seconds and changes it into coulombs. Now that we have coulombs in charge, that's how many coulombs of charge came into the solution of cobalt. We can change that into moles of electrons using the Faraday constant. That was where we had 96,500 coulombs in every 1 mole of electrons. Or 96,485. It's close enough to 96,500 though, that works. Now that we have how many moles of electrons came in, that's step number 4. When you're writing it, you may have thought, what do you mean by that? This is what it means. Notice the cobalt ion is a positive 2 ion. We're starting with cobalt 2. If I want to plate 1 mole of cobalt from cobalt 2, how many moles of electrons would I need to come in? It's cobalt positive 2 charge. So I would need 2 moles of electrons to plate a mole of cobalt from cobalt 2. So that's what our next step is. That's what I mean by use the oxidation number. Every 1 mole of cobalt, sorry, I'm now behind the board like that. That's the exploding egg. That would need 2 moles of electrons. You see that? Because there was a positive 2 charge, you need 2 electrons for every atom. That means if you want a mole of cobalt, you got to use 2 moles of electrons. All right, and finally, the last step is just simple, because the question is what mass of cobalt now? So we just use the molar mass from the periodic table. Every 1 mole of cobalt has a mass of 58.9, I think. 58.9. That's it. We just crank that on our calculator. And you're going to get, we can only have 2 sig figs, so you're going to get something really close to 16 and a half. So either side of 16 and a half, 16 or 17 is fine. Any questions about that? Let's take a look at one other example. I want you to try one and see if you can make your way through that whole stoichiometry process, and then we'll call it a day. So here's the next one. This one is not exactly the same, but it's good.